Very welcome everyone to our next session of the Fractal Geometry Seminar, and I have the great pleasure to introduce you our speaker Zoltán Buczolich from Buczolich University, and he will talk about purely unrectifiable sets and relevant stuff. Please.
Thank you for the invitation and the opportunity for giving this talk. Since the software I used for presentation was just now installed, I am working also as a guinea pig for working, so I apologize for any kind of software-related issues during my talk. I was at the beginning of February for 1 week in Hangzhou, China. I was invited to a geometric measure theory winter school, and the main topic of that school was rectifiability and pure unrectifiability. So I was speaking about my results related to this topic. And this was the time when Balázs contacted me about this talk, and it was a natural idea since I do not see any overlap between my audience in Hangzhou and this place. To speak about this, and I usually, here is the first issue. I need to, yeah. So here is the first part of the talk. Before I move to the outline of my talk, I would like to mention that the fractal percolation part of my talk is based on a joint paper with the Jarvenpás, Tamás, who is here, and Thomas Pétari. And what I did, that I am not doing exactly my talk from Hangzhou, because I was making a longer talk, as I usually do, and I was very unhappy that I couldn't speak about the second part of my talk. So now I was switching the second part and the first part. So in this talk, the first part is my survey about my older results related to regular and irregular sets on the graphs of functions. So this is this first part, and the second part is about fractal percolation, and it seems to be highly likely that I won't have enough time to cover everything I wanted, but anyway, this will complete the whole talk. So let me remind you some of the definitions. Rectifiable and unrectifiable sets. There are several equivalent definitions. So a Borel set in the d-dimensional Euclidean space is rectifiable if you can cover it by a countable family. Oops. So you can cover it by a, yeah, it doesn't work. It's not the software I use at the ELTE. So you can cover it by a countable family of Lipschitz maps such that the complement of the cover is of k-dimensional Hausdorff measure 0. There's a very nice theory of this in the plane, and if you read the first book of Falconer about fractal geometry, I really love those chapters. And the original theory, the d-dimensional theory, yes. So the original d-dimensional theory is due to Bezikovich, and it is in the plane, and in this case k equals 1, so you are speaking about one rectifiable set. There is another definition. You can see that over here there are Lipschitz maps, and the Lipschitz is not necessarily necessary. You can also use C1 k-dimensional submanifolds, which are much nicer than the Lipschitz map, and it is the same thing that H k almost all you want to cover by countably many such manifolds. I forgot to mention that the higher dimensional version is due to Matilda and many other people, but if I need to mention one name, I should mention him. So now comes the trick.
Let's close this should move.
Okay. So now the next concept, maybe I will shrink, no, it's a bit too much. So if a set is not rectifiable, then it is called unrectifiable. And there is the extreme case for being unrectifiable. So you say that an unrectifiable k-dimensional set is purely unrectifiable if its intersection with any k-dimensional rectifiable set is an HK null set. On the other hand, you can also see that the unrectifiability is equivalent to the fact that the intersection with the image of an arbitrary Lipschitz map, so if you look at the range of such map, is an HK null set. Oh, I see over here these blue lines are sticking.
So if you again click on the annotate, click on the annotate, and then click on the dust bin, trash bin. Sorry, trash bin. No, it's on the left-hand side. Place the trash bin. Here, hold on. Yes.
Yeah. So.
And I again close it if you.
And how can I just simply kill this, because probably it's better I am just not using it because it is quite confusing. So there are several versions of defining this. Over here you can see the Lipschitz maps. You can also use the fact that instead of Lipschitz ranges of Lipschitz maps, you can also use CK submanifolds in the same space, such that the k-dimensional Hausdorff measure of the intersections of the set with these k-dimensional CK submanifolds is of k-dimensional measure 0. Using this setup, one can use Fubini's theorem and easily obtain the following corollary, that if something is purely unrectifiable, then of course you can test it by one-dimensional intersections and you can integrate them. So one unrectifiability implies that it is also purely k unrectifiable for any integers k, because if you are intersecting with a two-dimensional manifold, then you can just integrate from the two-dimensional manifold the one-dimensional fibers. And there is one definition, at least it has turned out that this seems to be a quite recent definition and quite interesting. This is the one which we use for the fractal percolation result about pure alpha unrectifiability. So what happens if you are testing your set not with CK one-dimensional or higher dimensional function graphs, but you are testing it with Hölder functions. So just a little reminder that if you have an alpha between 0 and less or equal than 1, and you fix an h which will be something like the Lipschitz constant, and we say that a curve is h alpha Hölder continuous, well, you probably are very familiar with the definition. If the distance between gamma and gamma b is less than this constant h times the distance between a and b raised to the alpha's power. And well, a curve is h alpha Hölder if it is h alpha Hölder at every point, and it is alpha Hölder if you are dropping the assumption that you have a fixed constant h, but the constant h might change from point to point. So for every A, it is H, A alpha Hölder, but this H might depend on the choice of the A. And there is one more easy exercise. Usually when we are learning about Hölder maps, and this is the fractal dimension, the first information which you have, that if you have an H alpha Hölder curve, then if you are taking the image, so your curve is parameterized on the interval I, and you are taking the image of the set A, then here there is a reciprocal or alpha. So if you are interested, you know the Hausdorff, one-dimensional Hausdorff measure of the set A, then the 1 over alpha dimensional Hausdorff measure of gamma A is less or equal than this constant H, the 1 over alpha times the one-dimensional Hausdorff measure of A. So the Hölder maps are changing the dimension, and you need to use a different Hausdorff measure. And well, there were these H alpha Hölder curves. It is also an easy exercise to verify that if we have an alpha Hölder curve for some alpha between 0 and 1, then so in the case of the alpha Hölder curve, I remind you that this H, this constant H in the definition of the alpha Hölder might change from point to point. But if you have an alpha Hölder curve, then you can always cover it with a countable collection of curves such that each curve is I alpha Hölder. So it is not a serious problem, since anyway we are working with countable covers, that whether we work with H alpha, fixed H alpha Hölder curves, or just with alpha Hölder curves. And these considerations implied that the following definition makes sense. So a set A is alpha rectifiable if you can find alpha Hölder curves gamma I such that, and you can see that here there is the H, the 1 over alpha dimensional Hausdorff measure of the images of the interval I, so gamma I, you take the unions of the gamma I's, you take it away from A, and they are 1 over alpha in the 1 over alpha dimensional, 1 over alpha Hausdorff dimensional sense, they are almost covering the set A. And there is the opposite definition, is the purely alpha rectifiability, which means that if you take the image of any alpha Hölder curves, then A intersection with gamma I, according to the 1 over alpha dimensional Hausdorff measure, is 0. It is quite clear that if alpha is 1, this definition is just giving back the one rectifiable rectifiability and the pure one unrectifiability definitions. So the next thing is recalling the decomposition theorems. So if you have a Borel set which is of sigma finite k-dimensional Hausdorff measure, you can find always a decomposition of the set into a regular and an unrectifiable set. So the set E can be written as R union U, where R is a regular k-dimensional set and U is a purely unrectifiable set. And this also means that if you have a rectifiable k-dimensional set, then you can also obtain this as a disjoint union of the set EI, where E0 is of k-dimensional measure 0. This is the negligible part, and the sets EI are compact and they are C1 k-dimensional submanifolds for any I bigger or equal than 1. The other thing which also people like about working with rectifiable and unrectifiable sets, is the famous Bezikovich-Federer projection theorem. So you can consider the set of all k-dimensional planes in the d-dimensional space. It is the so-called Grassmann manifold, and you can put a measure on them, and you take a set E, which is a key set, which just simply means that it is a proper k-dimensional set, so it is of positive k-dimensional Hausdorff measure, and this Hausdorff measure is finite. And there are these very nice projection properties. So a set E in the d-dimensional space is, which is a K set, is purely unrectifiable if according to this measure of the Grassmannian, so there is this measure mu, almost every projection of this set is of k-dimensional measure 0. Of course, if you are not really familiar with the Grassmannian manifold and you are working in the plane, then you can put it much easier that if you just simply take a planar set E, it is an irregular set if for almost every directions the one-dimensional measure of the projection of the set is of Lebesgue measure 0. If you are just simply working with the directions, that the Grassmannian is just a circle, then you have these diametrically opposite points. There was also the other nice result when you are reading about irregular sets and regular sets in the plane, that if you have a regular one set, then its projection is of positive one-dimensional Lebesgue measure for all but at most one exceptional direction theta. It is quite clear that if you take a line segment, then it has one direction. It might have one direction in which you are just simply projecting it into one point, so you have this possibility of having at least one projection of 0 measure. So the first part of the talk is about regular and irregular sets on the graphs of functions. And the first example is the well-known Takagi function, which was a classical example of a continuous no-word differentiable function. And it is defined as the sum of these functions Gn, where G1 is just this green function, G2 is this blue function, G3 is this red function. So these are the distance functions from the dyadic rationals, where dn is k over 2 to the n minus 1. And you have this nice looking function. At the time of Takagi and van der Waerden, there was no Google Scholar or Messinet or AI, so the Takagi function was rediscovered several times. So it was discovered by Takagi in 1903. Then in 1930, van der Waerden studied something which has turned out to be in 1933 essentially equivalent to the Takagi's function, and in the 1950s, de Rham also rediscovered the Takagi function. In 1959, Jean-Pierre Cahan started to study the level sets of the Takagi function. He verified that the level set at 2/3, where 2/3 is the maximum of the Takagi function. And in high school, you got used to the fact that you have a smooth function, and usually the maximum is taken at 1 point or something like that. In this case, the situation is just the opposite, because the maximum is taken in a perfect, totally disconnected set of Lebesgue measure 0. Later, it was verified that this level set has Hausdorff dimension 1/2. And actually, out of the level sets of the Takagi function, this is the champion. So this is something a little bit against our common knowledge about the size of the maximum. At the time, in 2006, I was proposing a question for the Miklós Rejcer competition. Well, in Hungary, you don't have to introduce it too much. It lasts for 10 days, and there are some research level problems in it. So I was asking essentially the question that what can you say about the level sets of the Takagi function? So you are just simply looking at this set Ly equal consists of those x's where f of x equals y. And during the competition, there were 3 answers coming in. Well, the correct answer that it is finite, and there was one student verifying the correct answer. There was one student trying to verify that it is countably infinite, and there was one student trying to verify that it was uncountable. The one who came up with the answer that it is finite actually won the competition, but not depending only on my question. So now we regard the Takagi function of the 0-1 interval, and the one-dimensional Hausdorff measure in the plane will be denoted by this h1, and the Lebesgue measure on the real line by this little lambda, and pi x and pi y will be the projections onto the x and y axis. And if you take the Takagi function, then its graph can be decomposed in a very nice way into an irregular and regular one set. The irregular one set has the property that its projection onto the x-axis is 1, and the projection onto the y-axis is equals 0, and since it is an irregular one set, in almost every direction, it has a projection of 0 one-dimensional, 0 Lebesgue measure or 0 one-dimensional Hausdorff measure. The regular part of the graph of the Takagi function can be covered by the graphs of countably many monotone functions. The regular part is in a certain way responsible for the finite level sets, and the irregular part, as I mentioned earlier, it's a purely unrectifiable set. I have already discussed this, and now I want to give you a little sketch of the proof. So if you are looking at the functions converging to the Takagi function, you start up with this red function, and then you are adding the second function, and you end up with this yellow function over here, and you can see that there are these flat parts on the yellow function, and on top of the flat parts there is a similar copy of the Takagi function. Actually, if you are looking at these approximating functions, these are piecewise linear, and if you are looking at the derivative of these functions apart from those breakpoints where the derivative doesn't exist, then since you are always adding things which are of slope +1 or -1, you are actually ending up with a model of the symmetric random walk when you are looking at the derivatives. If you are looking at the development of x in days 2, then 0 is a +1 and 1 is a -1 for the slope. So we know by Poyar's theorem that the symmetric random walk is persistent, which means that infinitely often, for almost every x, you will have situations that the derivative is 0. So it means that for almost every x, infinitely often, you have a tiny, small copy of the Takagi function over the point. So if you want to go for this development, I am now writing this thing in a longer way on the board. So this capital X1 is the set of those points where infinitely often we have this slope 0, and nx1, nx kappa, and so on is just those indices the approximating function has zero derivative. So for example, on this picture, there is x0 over here. There is this flat part in this case, in the second approximating sum to the Takagi function, and then ix01 is denoting the interval on which you have a small similar copy of the Takagi function, and jx01 is just an interval of the same length as the base interval, and since the Takagi function is coming up only to the level, to the height of 2/3, this square is containing a similar copy of the Takagi function. It is always worth observing that here we have there is a second square on the other side which contains a symmetric, similar small copy of the Takagi function. And over here in the slide, there is just a complicated lengthy definition of this property that for x0, the ix0 kappa is just the sequence of intervals shrinking to x0, where you have this situation that a certain approximant to the Takagi function has zero derivative, and above that there is a small similar copy of the function. So there are these jx0 kappas over here, which are the y projections of these squares. And actually, it's very easy to see that if you have x0 in this set capital X1, then you have a shrinking sequence of squares, and each square contains a similar copy of the Takagi function. And actually, the irregular one set on the graph of the Takagi function is you are taking for a fixed kappa these little squares, and then you are taking the intersection for kappas, these nested squares. The lengths of these intervals are shrinking to zero, so it is very easy to see that this set will be a subset of the graph of the function. And using the symmetry property of the Takagi function, it is not difficult to see that, for example, over here we have these two 1/2 intervals, that these two squares are covering each other. So if you are looking at the projection of the irregular set onto the y-axis, then it is covered by these intervals jx1 kappa, and due to these repeated symmetry properties, there is a multiplier 2 to the minus kappa of the union of the lengths of the base intervals, but the lengths of the base intervals are 1, because this is just almost every point in the 0, 1 interval. So actually, the projection to the y-axis of this irregular set is less or equal than 2 to the minus kappa for every kappa. So this means that the projection onto the y-axis is 0. It requires a little more work, and I am not sketching it because I don't have time for that, that if you take other directions, then it will also give 0 measure, because at the moment we have just one direction in which we see that the projection is of Lebesgue measure 0, and one direction on the x-axis when we see that it is almost every point. So let's see now the regular part. So there are certain points which are not in these nested squares on the graph of the Takagi function. And what we can do that, so this is just a little reminder in green that what was the definition of the set x1. And we suppose that y0 is a level, it is one which is not in the intersection of the jx1 kappa union. So these were the projections of these squares on the graph onto the y-axis. And it is not in the intersection of the projection of this set, so it is not in the y projection of the irregular set on the graph of the function. This means that there exists a kappa depending on y0 such that it is not in the union of these jx1 kappas, which are the vertical sides of these squares which contain copies of the similar copies of the totally function. And then we just simply define a function g kappa x0, which is the corresponding approximating function. So if I want to define g1 of x0, then this is the spectral function of this image. So over here it was 1, this is this constant, and then when the first time it is getting, the tangent is getting horizontal, I am defining this to be a constant. This defines on a dense, dense set the function, and for the other points I extend the definition of this function by continuity. If you recall that we started with this triangle, over here the slope was +1, over here the slope was -1, and we were waiting for the first index when the approximating function has a horizontal tangent. This means that on this side we started up with derivative +1, and by the symmetric random walk, sooner or later you ended up the first time with a 0 derivative. But if you started up with a positive derivative, at the time when you are getting back to the 0 derivative, you always had non-negative slopes. So this means that this function is monotone increasing on the left side and monotone decreasing on the other side. If we are going for the function g2, then of course you have these monotones. So you are now on these parts where originally the first one had a horizontal part, and then there is a small copy of the g1 in any of these similar parts. So over there you also have these monotone parts within these squares. So actually these functions g1 and g2 are shown in purple on these images. So it is very easy to see that we have countably many horizontal parts for, say, the function g1. And if you are looking at for other values of y0, then the inverse image has two elements, one on the right and one on the left. So this means that by the Borel-Cantelli lemma, almost every y belongs only to finitely many intervals of this j x0 kappa -1. So by using the Borel-Cantelli lemma, one can verify that for almost every y in the range of the totally function, we have just finitely many intersection points. So this is about the level sets, which was at the Schweitzer competition. And if you are considering the points which are not in the irregular sets, then you can use these monotone functions defined by, well, I might say that by kind of a stopping time argument, which are monotone functions. So the regular part can be covered by the graphs of countably many monotone functions. Here there was a little homework because I was doing this talk at a winter school. So when we are looking at when we are speaking about regularity and irregularity of sets, there's a definition that you have covered them by Lipschitz functions or CK functions, but the monotone functions are not necessarily Lipschitz functions. So homework in the definition of regularity, we have Lipschitz maps. Why monotone functions are sufficient to prove that this is indeed a regular set. So you covered it by counting many monotone functions. So this was the first thing about regular and irregular sets of graphs or functions. And there was another thing I was dealing with a long time ago. These were the microtangent sets of continuous functions. So you denote by Qm the closed unit cube, and we take a compact subset on R to the M, and Fürstenberg defined the microsets of this set A. If you have the compact set and you are scaling onto this set. So you are just simply multiplying by gamma n, you can blow it up, and you can translate it. And you translate it to the closed unit cube. And then, of course, you are obtaining some closed subsets of the unit cube. So you can ask the question that whether in the Hausdorff metric you can select a convergent subsequence. So this is a kind of a tangent, concept of a tangent. And actually, the definition of the microtangent set of the graph of a function is indeed the following. So I denote by this qxy delta the closed cube of side length 2 delta, and centered at xy. And by q2, I will denote the standard one. So I take the one which is standard at the origin, like of this picture, and of side length twice 1, so this corners, upper right corner at 1, 1, and lower left corner at -1, 1. And if you have a compact set in R2, which is containing the origin, so it contains 0, 0, we say that it is central part, denoted by cent f, is the connected component which contains this point. Of course, if you are working with the graph of a function, it may happen that the graph is going out from this square, so we are just concentrating on the central part. And also we have this notation because we are always kind of moving to the origin. C minus from 1, 0 means that we have a continuous function on -1, 1, which takes at 0, 0, so crosses the origin. And then there is a rather natural definition when you are looking at a calculus textbook. Then for differentiable functions, for the derivative, you have a definition like this. So we take delta n bigger than 0, this will be a sequence converging to 0. And I denote by this capital FF x0 delta n the following. So I have the blue function on the left picture. And I am zooming onto a fixed point. The point is this red dot over there. And at different zoom levels, I am rescaling it to the standard Q2 rectangle, the graph of the function. So if I take this light magenta one, then the magenta part is the zoomed image of this. Actually, this is the actual zoom image of the function. And then the green function is the green blow up of the function, and so on. And then this provides you a set of compact sets in the cube Q2. And then we say that the set F is a microtangent set of F at x0. Notation F, capital F is in F empty x0. If you can find a sequence delta n going to 0 such that these compact sets are converging to the set F. Of course, since these graphs might go out of the square, this is also in this illustration, you can say that a set is a central microtangent set if you can find a delta n such that the central parts, so just the parts, the connected components which contain the origin, are converging to the set F in the Hausdorff metric. Of course, if you go back to the high school calculus textbooks, then if the function f is differentiable, then the microtangent set or the central microtangent set of the function is just simply a line segment of slope of the derivative. And this definition actually makes sense, and it is interesting when we are working with fractal functions where you don't have the derivative. So we say that x0 is graph-like or central graph-like microtangent point for the function f if you can find a continuous function on -1, 1, which takes the value 0 at 0, such that its graph is in the microtangent set of x0 or in the central microtangent set of x0. And GLNTF or CGLNTF denotes the set of graph-like microtangent points or central graph-like microtangent points of a function f. It is quite clear that the CGLNT contains the GLNT. And we say that x0 is a universal microtangent point if you take an arbitrary function g from c minus 1, 0, it is in the microtangent set. Well, it is not completely clear that if you take a fractal function, whether there is a function g to which you can converge in the Hausdorff metric. There are many functions, for example, I don't have too much time to discuss it. For the Brownian motion, for example, you don't have this limit at any point. Of course, if you are lucky, then you have a function, and you are very lucky if you have any function which is continuous on -1, 1. I denote by this UNTF the set of these very nice points that any function you can be approximated by a suitable sequence of zooms to the given point. And of course, there is the question that if you are taking the typical continuous function in the bare category sense, then what can you say? First observation that these sets GLNTF and CGLNTF are of sigma finite one-dimensional Hausdorff measure. And the result of Moldin and Williams says that if you are looking at the graph of the typical continuous function, then it is of Hausdorff dimension 1, but it is not of sigma finite one-dimensional Hausdorff measure. So this says that this universal, this GLNTF and CGLNTF points are just a minority on the graph of a typical continuous function. For most points, you cannot approximate the graph of a function by these different zoom levels on the graph. So yes, so most points are not that way. And then if you take a fixed continuous function between -1, 1, taking 0 at the 0, then the set of those continuous functions for which the projection, so the first information, I just go back, was just simply saying that for any function, for the typical continuous function, it is not likely that you have a point in GLNTF, so you can find a function g in the limit when you zoom in and you blow up the image. But on the other hand, these points have a full measure if you project them onto the 0, 1 interval. So for almost every x, if you are picking randomly according to the Lebesgue measure an x, then at that x you can find for a fixed g a microtangent point over that. It is also clear that, or not too difficult to verify, that if you fix the function g, then this GLNT-GF is a G delta set in the relative topology of the graph F. But if you have this for a fixed G, and you are looking using the fact that C minus 1, 1, 0 is separable, it's very easy to verify that there is a dense G delta set. So the typical continuous function has the property that almost every x is a universal microtangent point. So for almost every x, any graph of a continuous function can be approximated when you are zooming in. It is a dense G, this UMTF is a dense G delta subset in the relative topology of the graph of the function. And a typical point of the graph has this universal microtangent property. On the other hand, if you are denoting by G0 the identically zero function, then of course the CGLMT G0F is the GLMT G0S because the component which you have is the constant zero function in the center. And this UMTF already we saw had X projection almost everywhere. But if you project into the Y direction, it is quite similar to the Tokaji function. So there is a dense G delta set in C01. So for the typical continuous function, the projection of the universal microtangent points on the graph of F is zero onto the y-axis. So it is very funny that if you pick randomly the domain of the typical continuous function in X, then it is a universal microtangent point. But if you are going from the y direction, then you intersect the graph of the function at many points, but none of these points are universal microtangent points. So this is an interesting property. Actually, since you are adding Cx to a typical continuous function, it is still a typical continuous function. If you take any direction, so if you are going back to the Bezikovich-Federer projection theorem, if you take any direction, the projection of these universal microtangent sets is of measure zero. Only the x direction is almost every point. Any other direction is of measure zero. It is also interesting that Hanke and Petrushka proved that the packing dimension of the typical continuous function equals 2, and from the packing dimension point of view, this UMTF is sufficiently large, so the packing dimension of UMTF on the graph of the function equals 2. Maybe there is this one remark about the Brownian motion, that the Brownian motion is much wider than the typical continuous function. So if we take the Brownian motion path, then you don't have any function showing up. So this just simply says, I use the chalkboard because I had to struggle a little bit with that annotator. So the reason that for the Brownian motion is going good pretty fast when you zoom in. So the central parts are approximating only the vertical line segment, nothing else. So you cannot have this graph being approximated by the Brownian motion. And well, I think that I was doing the fractal percolation in Hangzhou, and I was doing the irregular one-sets on the graphs of functions in Budapest. So at least in these 2 halves, I am happy because I was doing my talk 8,500 kilometers apart. But anyway, thank you for your attention.
Thank you very much. Questions, comments? So on the
Yes.
Oh, I have a few questions. When did you change not the triangle like this, but you take another triangle basic?
There are many variants of the Tokaji function. So there is I mean that for with respect to the irregular sets and irregular one sets, well, it depends. So in certain cases you might be able to preserve something, in certain cases not.
But in the case that you see the vertices on the rational number, it changes a lot, or?
Well, I think that what is important for us was the symmetry property.
The symmetry.
And there is some problem with the symmetry. But yeah, it can be studied.
Okay, thank you.
We take the same question.
Okay, sorry.
Okay, more questions? Online? Maybe? Other question? No? Okay, if not,